I want to do a quick demonstration of the right-hand rule. This is called an oscilloscope, and it is for measuring voltages, is what it can do. It can measure voltages, it can measure both AC and DC voltages, and it gives you a nice graphical display of what that looks like. The way this graphical display works is this is an old school device here. It's almost like an old television. There's actually a cathode ray tube inside here. And what a cathode ray tube does is it accelerates electrons to a very high speed, and they fly towards the front of the screen. And when they hit, there's some chemicals on the front of the screen, and when the electrons hit that surface, then those chemicals glow. So that's what happens. So electrons are accelerated towards you at a high speed. When they strike the screen up here, then they cause a different something to glow, and that's how you can see this visualization here. So it's an electron beam. That means we have moving electrons. We ought to be able to influence them or create a force on them with a magnet. Let's just see if we can. So I have this magnet, and we want to think that the poles are on the ends here, either north and south or opposite, because that's typically how bar magnets are set up. But in this particular case, we see the north being attracted, north side of my compass being attracted there, but, if I kind of twist it around there, I can also get the south side pointing there. So it's behaving sort of erratically. It turns out that the north and the south poles of this magnet are here and here. Which is which? Well, let's see. So you see we got north attracted there, and as I go around, south is attracted there. So, which is my north and which is my south? Well, we know that opposite poles attract, so the north side of my compass is attracted to the south side of my magnet. The south side of my compass is, of course, attracted to the north side of my magnet. So that means north is here, and we'll put a little red piece of tape there to make sure we remember. That means the south should be here. Let's double check. Indeed, north is attracted to south, and south is attracted to north. Okay, so now we're back. We're looking back at the oscilloscope. What I'm going to do is I'm going to bring my magnet to this side of my cathode ray tube, and I will bring it so that the north pole is closest to the cathode ray tube and the south pole is farthest. So it will be the north pole here and the south pole here. And I want you to predict for these electrons moving towards you. Do we expect the beam to move down, up, nothing at all, something different? Why don't you think about it? Get out your right hand, try right-hand rule number 2, see if you can't make a prediction. Well, let's just see what happens. Here I have my magnet. Again, north is marked red, south is marked white. Let's bring the north pole in and see what happens. Indeed, the beam is deflected down. Let's see if we could have predicted that with the right-hand rule. Remember that the magnetic field points out of north poles and towards south poles, which means that with the north pole facing this way, my field is in this direction. The velocity is towards you, which means that the force, by the right-hand rule, on a positive charge would be up. However, these are electrons. Electrons have a negative charge, and so we flip our answer, and we get the correct answer that the force on them